Welcome to qnawire.
In this problem, we're given an infinitely long line of charge with the linear charge density 5 into 10 to the negative 12 coulombs per meter, and there's a proton at a distance r away from the line of charge moving towards it with the initial speed 3 into 10 to the 3 meters per second. Now for the first part, we need to calculate the proton's initial kinetic energy. So that would be E is equal to 1/2 mv squared, and that just gives us E is equal to 1/2 times the mass of the proton, which is 1.67 into 10 to the negative 27 kilograms, times the velocity, that is 3 into 10 to the third power, the whole squared. Now we can go ahead and evaluate this expression using a calculator, and that gives us E is equal to 7.51 into 10 to the negative 21 joules. So that is our answer to the first part. Now for the next part, we have to find how close the proton can get to this line of charge. For that, what I like to do is find the potential at R. And since this is an infinitely long line of charge, we can enclose it in a cylinder that I've drawn with a dotted line. So we can enclose it in a cylinder of radius r, and let the cylinder have the length L. Now since the line is infinitely long, the electric field is directed radially outwards from the cylinder. So if you draw a cross section of the cylinder, so I'll do that by drawing a circle. Then we will find out that since the electric field is being directed radially outwards, it makes an angle of 90 degrees with the surface of the cylinder. Now, we can recall Gauss's law that states that the closed surface integral of E dot ds is equal to the total charge enclosed divided by epsilon naught. So since the electric field and the surface ds are parallel to each other, so the surface vector is actually perpendicular to the surface itself, they're parallel. That means that E dot ds is actually equal to E ds. So that gives us surface integral of E dot ds being equal to E ds equals the charge enclosed divided by epsilon naught. Now, since this is a circle and the electric field travels the same distance throughout the entire surface, the electric field at the surface is a constant. So we can actually pull that out of the surface integral And what we're left with is basically the surface integral of ds that will simply be equal to the surface area of our Gaussian surface, which is the cylinder. Now, since the cylinder has a length L and a radius R, the surface area is actually given by 2 pi R times L, and the total charge enclosed is the length of the wire enclosed, which is L, times the linear charge density. So we'll go ahead and make these substitutions into our equation. So Q equals lambda L. This entire thing is divided by epsilon naught. And S is just 2 pi R times L. Now we can cancel the L's on both sides, and what we get is E is equal to lambda over 2 pi R epsilon naught. Now our potential is actually given as the negative integral from a point R1 to R2 of the electric field times dr. Now we know that R1, which is the initial distance, is 18 centimeters, or 18 divided by 100 meters in standard units. And we can leave R2 as it is because that's the radius we have to find out. So that will be the total work done per unit charge in transporting the electron from its initial position to its final position. And we can substitute in E is equal to lambda divided by 2 pi R epsilon naught dr, and we can pull all the constants out of the integral. So that's negative lambda divided by 2 pi epsilon naught times the integral from, so 18 divided by 100 is just 0.18 to R2 of 1 over R dr, and that is equal to the potential. Now the integral of 1 over R is simply the natural log of R, and the limits go from 0.18 to R2, and that gives us the natural log of R2 minus the natural log of 0.18. And using the properties of logarithms, we can actually write it down as the natural log of R2 divided by 0.18. Now the total work done by the field is actually equal to the potential times the charge. So the potential times the charge is simply equal to negative lambda q sub p, because the particle is a proton, so it will be multiplied with the charge of the proton, divided by 2 pi epsilon naught times the natural log of R2 divided by 0.18. Now the total potential, rather the total work done at the final point, will be equal to the kinetic energy that we just calculated in the previous part. So 7.51 into 10 to the negative 21 joules. So all of the kinetic energy, 7.51 to 10 to the negative 21 joules, will be converted into potential energy. We know that lambda is equal to 5 into 10 to the negative 12 coulombs per meter. The charge of a proton is 1.60 into 10 to the negative 19 coulombs. 2 pi stays as it is, and epsilon naught is 8.85 into 10 to the negative 12 in SI units times the natural log of R2 divided by 0.18. That gives us the natural log of R2 divided by 0.18 is equal to 7.51 into 10 to the negative 21 times 2 pi times 8.85 into 10 to the negative 12, and there's a negative sign over here, divided by 5 into 10 to the negative 12 times 1.60 into 10 to the negative 19. And we can go ahead and evaluate this entire expression, and that gives us the natural log of R2 divided by 0.18 as being equal to 0.522, and we can exponentiate both sides and we get R2 divided by 0.18 is equal to e to the 0.522 power, which is equal to 1.685. Sorry, I missed a negative sign over here, so there's a negative sign, and this instead evaluates to 0.593, and we can go ahead and cross multiply to get R2 is equal to 0.18 times 0.593, and that gives us R2 is equal to 0.107 meters, or 10.7 centimeters. And that is our required answer for the last part.